Okay, in today's lecture, we're going to cover the next part of the section 6.3 material on Taylor and Maclaurin series. So the primary focus for today's lecture will be on the Maclaurin series for a function. So recall that a Maclaurin series for a function is simply the Taylor series for that function centered at 0. So using the formula that we had derived for the Taylor series of a function centered at a, replacing a by x equals 0, we have the following definition for the Maclaurin series of a function. So this is a way to represent a function, f of x, as a power series centered at 0. So here, our formula for the nth coefficient of this power series is the nth derivative of f evaluated at 0 divided by n factorial. So recall this notation here, f sub n, or f superscript n of 0 is used to denote the nth derivative of our function f of x, and we're evaluating at 0 since this is defined as the Taylor series centered at 0. So recall that anytime a problem is asking you to find a Maclaurin series for a function, it's really the same problem that we've been working with. We want to find the Taylor series for that function. The only difference is for a Maclaurin series, we're centering at 0 specifically. So let's look at an example of this. In our first example, we're asked to find the Maclaurin series for the function e to the x, and then determine its radius of convergence. So we know for any of these Taylor or Maclaurin series problems, we need to find an expression for the nth derivative of our function. So our first step is always to find the first several derivatives until we can establish a pattern. So in this example, if we're working with the function f of x is e to the x, then our first derivative, f prime, would be e to the x. And then our second derivative, f prime of x, would also be e to the x. Our third derivative would also be e to the x. And so in general, we know for e to the x, any higher order derivative would be the original function. So in general, any nth derivative of this function would be given by e to the x. So once we have this expression for our nth derivative, if we're looking for the Maclaurin series of this function, we're centering the Taylor series at 0. So we're going to evaluate this nth derivative at x equals 0, which would give us e to the 0 or 1. Now, once we have this expression, we can substitute directly into our formula for the Maclaurin series. So we have our function f of x can be represented as the sum from 0 to infinity of 1 over n factorial times x to the nth power, or more concisely, the sum from 0 to infinity of x to the n divided by n factorial. So this, again, is a representation of the function e to the x as a power series centered at 0. And we want to know the second half of this question, what is the radius of convergence? So where can we represent e to the x in terms of this power series? So to find the radius of convergence for a power series, we typically use the ratio test. And to use the ratio test, we would be looking at the limit as n approaches infinity of the absolute value of the ratio of our n plus 1 term. So that would be x to the n plus 1 over n plus 1 factorial. And then we divide by the nth term in our series, but as usual, our nth term is a fraction. So dividing by that fraction is the same as multiplying by its reciprocal, n factorial over x to the nth power. So this leaves us with the limit, as n approaches infinity, of the absolute value of, well, let's see which terms we're left with. So if we start with our x to the n plus 1 over x to the n, we can cancel n factors of x, and that leaves us with x to the first in our numerator. And then looking at the quotient n factorial over n plus 1 factorial, we're left with division by n plus 1. So we can pull any terms not involving n out in front of our limit. So in this case, we would have the absolute value of x times the limit as n approaches infinity. And when we pull out that absolute value of x, we're left with 1 over n plus 1. Now, as n becomes large, this fraction, 1 over n plus 1, decays to 0. So we have a limiting value of 0, which is less than 1. And notice that we get that limiting value of 0 regardless of what this constant absolute value of x was out in front of the limit. So we will have a 0 limit, which is less than 1, for all values of x on the real number line. So we can say that our radius of convergence is then infinite. This power series converges for every value of x on the real number line, so the interval of convergence is negative infinity to infinity, and our radius of convergence would be infinite. So what that means is that this power series expression that we found for e to the x is valid for any value of x. So if I wanted to represent, say, e cubed as a power series, I could just plug 3 in for x in the expression that we found for this power series, and it's a valid representation of e cubed. And this says I can do that for any such value of x. So this Maclaurin series for e to the x, you will want to have memorized. I'm going to put a little star by this in the lecture notes, and let's make a note to yourselves that you want to memorize the form for this Maclaurin series. We'll see some examples a little bit later in today's lecture where it'll be useful to have this expression memorized. But for now, let's look at some Maclaurin series for other functions that have a particularly nice Maclaurin series. The next one we'll consider is the function f of x equals sine x. So we want the Maclaurin series for that function and its radius of convergence. So as for all of these Taylor or Maclaurin series problems, our first step is to find the first several derivatives of this function until we can establish a pattern. So in this example, if we have the function f of x is equal to sine of x, and we start taking derivatives, then our first derivative, f prime of x, is cosine of x. The second derivative, f double prime, would be negative sine x. Our third derivative, f triple prime, is negative cosine of x, and our fourth derivative would be given by positive sine of x. And then notice that this fourth derivative is the same as the original function. So our fifth derivative will also be cosine of x, the same as the first derivative. Our sixth derivative will be the same as the second derivative, negative sine of x, and so on. This pattern is going to keep repeating. So if we are interested in a Maclaurin series, we need to know what is the nth derivative at 0. So let's try evaluating each of these derivatives that we found at x equals 0. So starting with our original function, f of 0, or sine of 0, would be 0. F prime of 0 is cosine of 0, or 1. F double prime of 0 would be negative sine of 0, or 0. Our third derivative at 0 is negative cosine of 0, which would be negative 1. And then our fourth derivative at 0 is sine of 0, which is 0, and that pattern will repeat since our derivatives were cycling through the same four functions over and over. The values of these derivatives at x equals 0 will cycle through the same values: 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on. So let's see if we can write out an expression for this Maclaurin series for sine of x. So here, f of x, recall the general formula for our Maclaurin series, is the sum from n equals 0 to infinity of the nth derivative of our function at 0 over n factorial times x to the nth power. So if we were to write out the first few terms, well, when n is equal to 0, we would have f of 0, which was 0. Then our next term, when n equals 1, we would have the first derivative at 0, which was 1, divided by 1 factorial, which is 1, times x to the first. So we would have 1x to the first power. Then moving to the next term in our Maclaurin series, well, the next term has a coefficient of the second derivative, f double prime of 0, which was 0. So there is no x squared term here. Then the next term that we see would have a coefficient f triple prime of 0, which we found to be negative 1. So I have a negative 1 divided by, for the third derivative term, we are dividing by n factorial, or 3 factorial, times x to the nth, so we would have x cubed. Then our next term, corresponding to n equals 4, well, the fourth derivative of our function at 0 is again 0. So there is no x to the fourth term. And that's the same value as our original function at 0. So then moving to n equals 5, we have the same value that we had for our first derivative, that is a positive 1. And then we're dividing by 5 factorial times x to the fifth. Then for our next term, we would have the same coefficient for the sixth derivative as we would for our second derivative at 0, which was 0. So in other words, there is no x to the sixth term. And then our x to the seventh term would be the same value as the third derivative at 0. That is negative 1 divided by 7 factorial times x to the seventh, and we would keep getting more and more terms if we keep adding each expression individually. But at this stage, we start to see a pattern emerge for our series. So let's see if we could write this using the sigma notation. So here we would have the sum from n equals 0 to infinity, and let's see if we can come up with a pattern here. So notice that, first of all, these terms that we've written out for our Maclaurin series are alternating in sign. They're positive, negative, positive, negative, positive, and so on. So to capture this alternating sign, we can use the general expression, negative 1, either to the n or the n plus 1 power. And we notice that the terms corresponding, well, here we only have odd powers, so let's maybe start by looking at how we're going to express odd powers of x. So since we only have odd powers of x appearing, that is x to the first, x cubed, x to the fifth, x to the seventh, so on, well, any odd power of x can be written as x to the 2n plus 1. And then notice that we're dividing by that same value factorial. So for x to the first, we were dividing by 1, or 1 factorial. For x cubed, we divided by 3 factorial. For x to the fifth, we were dividing by 5 factorial. For x to the seventh, dividing by 7 factorial, and so on. So whatever the power of x is, we were using the general term 2n plus 1. We are dividing by that same quantity, 2n plus 1 factorial. So now, to capture this alternating sign a little more accurately, well, the first term that we had in our Maclaurin series was x to the first power. So if we're using the general expression x to the 2n plus 1, then that first term corresponds to n equals 0, so that we would have x to the first here. And we know that we want that to be positive, so we're going to make this the nth power, so that when n is 0, we have a positive 1. And then moving to our next term, when we have x cubed, that would correspond to the value n equals 1. So if we have negative 1 to the first, that would give us that negative term that we're after. So this would be the Maclaurin series for the function sine of x. So for this function, sine of x, we have a pretty nice expression for the power series representation. So I'll make another note here that this is another one that you will want to have memorized. And in the last part of the question, we're asked what is the radius of convergence for this power series. So again, making use of the ratio test, we would look at the limit as n approaches infinity of the absolute value of the ratio of our n plus 1 and nth terms. So for the n plus 1 term, we have negative 1 to the n plus 1 times x to the 2n plus 3. When we replace our n by n plus 1 and distribute that 2, we have 2n plus 2 plus 1, or 2n plus 3 as our exponent, over 2n plus 3 factorial. And then we divide by the nth term, but since it's a fraction, that is equivalent to multiplying by its reciprocal. 2n plus 1 factorial over negative 1 to the nth times x to the 2n plus 1. So this leaves us with the limit as n approaches infinity of the absolute value of, let's see which terms remain. So the ratio of our negative 1 terms, if we cancel n factors of negative 1, we have a negative 1 to the first for our numerator. Looking at the x terms, our x to the 2n plus 3 over x to the 2n plus 1, if we cancel 2n plus 1 factors, we're left with x squared for our numerator. And lastly, our ratio of 2n plus 1 factorial over 2n plus 3 factorial leaves us with a 2n plus 3 times 2n plus 2 as our denominator. So again, as with our last example, if we pull out anything not involving n in front of our limit, we have the absolute value of x squared times the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. So this limit, as n gets larger, we have 1 over a larger and larger quantity, so this ratio is approaching 0. So regardless of the value of the absolute value of x squared out in front, we get a 0 limit which is less than 1. Again, that holds for all values of x which are real numbers. So our radius of convergence for this Maclaurin series is again infinite. So that means that the sine function, sine of x, can be represented by this power series that we found for every value of x. So let's look at another one. This next one, very similar. We have the Maclaurin series for cosine of x and determine its radius of convergence. So this one is very similar to sine. If we start by taking the first several derivatives of our function, which was f of x equals cosine of x, we have f prime is negative sine x. The second derivative, f double prime of x, is negative cosine x. Our third derivative is equal to positive sine x. And our fourth derivative would then be equal to cosine of x, which is the same as our original function. So all of the higher derivatives will keep cycling through these same four functions, positive or negative cosine of x. Now, since we're asked about a Maclaurin series here, we're centering our Taylor series at 0. So if we evaluate each of these derivatives at x equals 0, we have the original function, f of 0, is cosine of 0 or 1. F prime of 0 would be negative sine 0 or 0. Our second derivative at x equals 0 is negative cosine of 0, so that is negative 1. Our third derivative at x equals 0 is sine of 0 or 0. And our fourth derivative at 0 is cosine of 0, which is 1. And again, since these derivatives were cycling through the same four values, our derivatives evaluated at 0 will cycle through the same values. 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so on. So as we did with our last example, let's look at the first few terms of our Maclaurin series. That is the sum from 0 to infinity of the nth derivative at 0 over n factorial times x to the nth power. So here, writing out our first few terms, starting with n equals 0, we would have the 0th derivative, or the original function, evaluated at 0, which is 1, divided by 0 factorial, which is 1, times x to the 0, which is 1. So our first term of this Maclaurin series will be 1. Then our next term, corresponding to n equals 1, we would be looking at f prime of 0, which is 0, so there is no x to the first term. Now for our next term, when n equals 2, we're looking at f double prime of 0, which was a negative 1, divided by 2 factorial times x squared. Then moving to our next term, when n equals 3, well, our third derivative at x equals 0 was 0, so there is no x cubed term. And then when n equals 4, we have our fourth derivative at 0 was a positive 1, We're then dividing by 4 factorial, multiplying by x to the 4th. Then our next term would be the 5th derivative. When n is 5, we get the 5th derivative, which would be the same as what we had for the first derivative at 0. So since that coefficient is 0, there is no x to the 5th term. And then our x to the 6th term, well, the 6th derivative of our function at 0 is the same as the second derivative at 0. So we have a negative 1 over 6 factorial times x to the 6th. And as with the last example, we start to see a pattern emerging here. So let's see if we can express this using sigma notation, say as the sum from n equals 0 to infinity. So again, let's start maybe with the power of x here. We notice that the only powers of x which are appearing are the even powers. That is x to the 0th or 1, x squared, x to the 4th, x to the 6th, and so on. So any even power of x can be described as x to the 2n, where n is some integer. So if we are starting our series at n equals 0, our first term would be x to the 0 or 1. Now, whatever the power of x is, in this case, we had x squared, x to the 4th, x to the 6th, only the even powers. Notice that we are dividing by that same value factorial. That is 2 factorial, 4 factorial, 6 factorial, or in general, for the x to the 2n term, we are dividing by that same power, 2n factorial. And the last thing that we need to capture here is the alternating sign. Again, our terms are positive, negative, and so on as we move through our summation. So we're going to have negative 1 to some power, and if our first term of this series corresponds to n equals 0, and we want it to be a positive 1, we would take negative 1 to the nth power. So this would be a power series representation of cosine of x. It is centered at 0, so this is the Maclaurin series for cosine of x. And again, I'll mention that you'll want to have this one memorized. Now in the last part of this example, again, we're asked to determine the radius of convergence. So making use of the ratio test, we're looking at the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1 times x to the 2n plus 2 over 2n plus 2 factorial, divided by the nth term, or multiplying by its reciprocal. We have 2n factorial over negative 1 to the nth times x to the 2n. So this gives us the limit as n approaches infinity of, well, let's see which terms remain. So taking the quotient of the values, of these powers of negative 1, if we cancel n powers of negative 1 on top and bottom, we're left with negative 1 to the first in our numerator. Looking at the ratio of our x values, x to the 2n plus 2 over x to the 2n, well, if I cancel 2n powers of x, I'm left with x squared for my numerator. So we have a negative 1 x squared. And then our ratio of the factorials, 2n factorial over 2n plus 2 factorial, leaves us with a 2n plus 2 times 2n plus 1 for our denominator. So as with the previous example, anything not involving an n, I can pull out in front of our limit, and I have the absolute value of x squared times the limit as n approaches infinity of 1 over 2n plus 2 times 2n plus 1. And as n becomes large, this ratio, again, decreases to 0, no matter what the value of x squared was out in front. So we get a 0 limit, which is less than 1, for all values of x, which are real numbers. So that implies that our radius of convergence for this power series is again infinite. So we can represent the cosine function, cosine of x, in terms of this Maclaurin series for any value of x that we want. So in our next example, we'll start looking at finding the Maclaurin series for functions which are related to these Maclaurin series that we found for e to the x, sine x, or cosine x, and start looking at some applications. So before we jump into some applications, let's look at how to get Maclaurin series for certain related functions. So in this next example, we are asked to find the Maclaurin series for e to the x cubed. So one way that we could approach this problem is by finding the first several derivatives of this function, evaluating them at 0, and seeing if we can establish a pattern. But if you start that approach, you see that it becomes pretty difficult very rapidly because you have to make use of the product and the chain rule after you found your first derivative to get any higher derivative. It gets very tedious. But if we recall what our Maclaurin series was for e to the x, we can exploit that. So what I would start by doing here, I see that I have a function which is similar to e to the x power. The only difference is it's e to the x cubed. So let's recall the Maclaurin series for e to the x, which was the sum from n equals 0 to infinity of x to the n divided by n factorial. So if I'm looking for e to the x cubed, well, I can just replace my x in the Maclaurin series for e to the x with an x cubed instead. So here we would have the sum from n equals 0 to infinity of x cubed to the nth power over n factorial, or, making use of properties of exponentials, this x cubed raised to the nth is the same as x to the 3n, and then we're dividing by n factorial. So this would give me a Maclaurin series representation for e to the x cubed right away, as long as I was remembering what the Maclaurin series for e to the x was. So that's why it's useful to have those certain ones memorized, because we can get Maclaurin series for these other functions directly from those pretty easily. All right, so let's look at another one. In the next example, we are asked for the Maclaurin series for x times cosine of x cubed. So I see that it's sort of related to the cosine function. It's cosine of x cubed, and then I'm multiplying by x out in front. So let's start by finding the Maclaurin series for cosine, and then see how we can build up to get the Maclaurin series for this function. So first, let's recall that cosine of x can be represented as its Maclaurin series, which was the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. So if we're interested in the function x times cosine of x cubed, Well, let's start by replacing our x in the Maclaurin series for cosine by x cubed. So I still have this constant x out in front of the function, so I have x to the first, and then the Maclaurin series for cosine of x cubed would be the sum from n equals 0 to infinity of negative 1 to the n times x cubed to the 2n power over 2n factorial. Or, making use of properties of exponentials, we have x times the sum from 0 to infinity of negative 1 to the n times x to the 6n over 2n factorial. And then to simplify a bit further, this factor of x to the first that we have out in front, I can bring inside of the summation, that is, distribute it through the sum, and group it with my x to the 6n power. So this would give me the sum from 0 to infinity of negative 1 to the n times x to the 6n plus 1 divided by 2n factorial. And that would be the Maclaurin series for the given function. Now this is much easier than trying to find the Maclaurin series directly by looking at the first several derivatives of this function. Again, if you try to take the first few derivatives of that function and evaluate at 0, you see that it gets pretty tedious to establish the pattern. But if we remember the Maclaurin series for cosine, then we can get this expression immediately. So let's look at another one similar to this. In the next example, we want the Maclaurin series for x squared times sine of x over 2. So as soon as we see that our function involves the sine function, let's start by looking at the Maclaurin series for sine of x, and then build up to the Maclaurin series for this related function. So first, if we look at the Maclaurin series for sine of x, recall that it is given by the sum from 0 to infinity of negative 1 to the nth times x to the 2n plus 1 power all over 2n plus 1 factorial. So if we are interested in the function x squared times sine of x over 2, well, we have a factor of x squared out in front of our sine function, and instead of having sine of x here, we replaced our argument of sine with x over 2. So in our Maclaurin series for sine x, let's replace that x with x over 2 and see what we have. So we end up with the sum from 0 to infinity of negative 1 to the nth times x over 2 to the 2n plus 1 power all over 2n plus 1 factorial. So simplifying a bit, we have an x squared out in front times the sum from 0 to infinity of negative 1 to the n. And now using properties of exponentials, if I have a quotient which is being raised to some power, that is the same as taking the quotient of the powers. That is, I would have x to the 2n plus 1 divided by 2 raised to the 2n plus 1. And then I still had my factor of 2n plus 1 factorial in the denominator. Now in my last step, to simplify a bit further, this factor of x squared that we had out in front of our series, if I distribute it through the sum and group it with my x to the 2n plus 1 power, then I have the sum from 0 to infinity of negative 1 to the nth times x to the 2n plus 3 power all over 2 to the 2n plus 1 times 2n plus 1 factorial. So this would be the Maclaurin series for the given function. So we see that as long as we have our Maclaurin series for e to the x, sine x, or cosine of x memorized, we can find the Maclaurin series for other functions which are related to these by making use of that known Maclaurin series. So in our next example, we will consider some other applications of Maclaurin series. In particular, we can use these series to approximate a definite integral by making use of a power series. So as our first example of this, let's consider the following. We are given a definite integral from 0 to 1 of cosine of x squared with respect to x. Now, normally, to evaluate definite integrals, we would find an antiderivative for our function, in this case cosine of x squared, and then evaluate it at the endpoints, 0 and 1. But using the techniques which we've learned in our course, we do not have a method for finding an antiderivative of cosine of x squared analytically. So none of our techniques work. A substitution doesn't work, integration by parts, partial fractions, trig substitution, none of these methods will work here. So if we cannot integrate this function directly, let's try to express this in terms of a series. So our first step here will be to find a series representation of the function cosine of x squared. So using the work that we had done in our previous examples, well, we know an expression for the Maclaurin series of cosine of x. Cosine of x is given by the sum from 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. So if we're looking at a Maclaurin series for cosine of x squared, we take the Maclaurin series for cosine and replace the x by x squared. So we have x squared to the 2n over 2n factorial, or simplifying a bit, this is the sum from 0 to infinity of negative 1 to the n times x to the 4n over 2n factorial. Now we're supposed to integrate this function. So let's look at our definite integral. Here, the integral from 0 to 1 of cosine of x squared with respect to x would be found as the integral from 0 to 1 of its Maclaurin series, which was the sum from 0 to infinity of negative 1 to the n, x to the 4n over 2n factorial with respect to x. So using our work from section 6.2, we know that we can integrate this summation term by term. That is, I'll have the sum from 0 to infinity of my coefficient, negative 1 to the nth, over 2n factorial, and then my antiderivative for x to the 4n power with respect to x would be x to the 4n plus 1 divided by 4n plus 1. And since this is a definite integral, I don't need a constant of integration, but I'm taking this series and evaluating from x equals 0 to x equals 1. So when I substitute 1 in for x, I have the sum from 0 to infinity of negative 1 to the nth times 1 to the 4n plus 1, which is 1, divided by 2n factorial times 4n plus 1. And then we subtract what we get when we plug in 0 for x. But since this was a Maclaurin series centered at 0, when I plug in 0 for x, the entire series is 0. So I'm left with the following expression, which would be a representation of this definite integral as an infinite series. Now the question is, what is the sum of this series? If we wanted the true value of this definite integral, I would need to know the sum of this series. But in general, we don't know how to find the sum of infinite series unless they're geometric or telescoping. So instead, maybe we could approximate the sum of this series. So in part B of this example, we are told to use the sum of the first 3 terms to approximate the sum of the series, which is our integral, and then determine how accurate that approximation is. So here we had the sum from 0 to 1 of cosine of x squared dx was given by the sum from 0 to infinity of negative 1 to the nth divided by 2n factorial times 4n plus 1. So if I'm using the first 3 terms to approximate this sum, let's see what we have. So here, our first term corresponds to n equals 0. So plugging in 0 for n, we have negative 1 to the 0, which is 1, divided by 0 factorial, which is 0, times 4n plus 1, which would be 1. So we get 1 over 1, or just a 1 for that first term. Then we are adding our next term when n equals 1. Well, we have negative 1 to the first, so negative 1, divided by 2 factorial, which is 2, times 4 times 1 plus 1, which would be 5. Then moving to our next term, when n equals 2, we have negative 1 squared, which is positive 1, over 4 factorial, times 4 times 2 plus 1, which would give us a 9. So here we have the sum of the first 3 terms of this series. And this would be an approximation. If we simplify a little bit, let's write it as 1 minus 1/10 plus 1 over 4 factorial is 24 times 9. So whatever this value, this fraction reduces to, would be an approximation for the value of this definite integral. And then we're asked how accurate this approximation is. So anytime we're determining accuracy in an nth partial sum approximation, we're going to use a remainder estimate. And notice that this series is an alternating series. It involves this factor negative 1 to the nth. So by making use of the remainder estimate, for alternating series, the error in this approximation is given by the absolute value of the remainder in my nth partial sum approximation. So here we were using the sum of the first 3 terms to approximate our series. Now, since our initial terms started at n equals 0, our third term in this partial sum approximation corresponded to n equals 2. So we had our first term was n equals 0, n equals 1, then n equals 2. So the error here is given by the absolute value of R2, which by the remainder estimate is bounded above by A3. That is the third term in our series, or the term corresponding to n equals 3. So plugging in n equals 3 to our series, we have 1 over 6 factorial times 13, which reduces to 1 over 6 factorial is 720 times 13. So our error in this approximation is at most 1 over 720 times 13. So we have a very small error just by looking at the first few terms of our series as an approximation. So in this part of the lecture, we found or looked at how to find the Maclaurin series of a function, which again is just the Taylor series centered at 0. And we derived expressions for the Maclaurin series of some basic functions, namely e to the x, sine x, and cosine of x, and started to see how we could find Maclaurin series for certain related functions, and then maybe have some applications of integrating these functions, making use of Maclaurin series, and using an nth partial sum approximation to estimate the value of some definite integral. So we'll keep moving forward with this in our next lecture, and see some other applications of Taylor and Maclaurin series and how we can use them to approximate the values of certain